Hi everyone, let's continue with modeling periodic behavior. So we have so far completed the first 5 lessons, and this one is going to be lesson 6 and lesson 7. So in this lesson we will work with radians and arc lengths. Our lesson objectives are that we will use degrees and radians to measure angles. We will also talk about another way of locating a point on a plane. We will talk about arc length and radius relationship. We will calculate arc length using the equation theta equals S over R, or S equals R theta. And if we are working in degrees, we will rewrite that equation in a different form. The last one is we are going to visualize different sizes of angles in radians. The vocab for this lesson is going to be polar coordinates, radian, and arc length. Okay, let's get started with radian. So if I have a circle of radius r and I measure an arc length of the same length r, then the angle that this arc length makes with the center is 1 radian. Now if I repeat that segment a little more than 3 times, and it's exactly 3.14 times, actually pi times, then I will get half of a circle. If I double that, I will end up with the entire circle. And that is how we know that the total angle of a circle is 2 pi radians. Okay, so let's talk about comparing radians and degrees. Now we know the total angle of a circle is 2 pi radians. We also know that is 360 degrees. We know degrees is written as a little dot that is a superscript on your measurement, and radians is written as RAD. Okay, so if 360 degrees equals 2 pi radians, then we can use a conversion factor of 180 degrees over pi radians, or pi radians over 180 degrees, to convert from degrees to radians or radians to degrees. Okay, so here are a few examples. Let's first work on degree to radian conversion. So if I have a 90-degree angle and I want to convert it into radians, I will multiply it by my conversion factor. Now my conversion factor is either pi radians over 180 degrees or 180 degrees over pi radians. Which one to use depends on what unit do you want to get rid of. We want to get rid of degrees, so we want degrees in the denominator of my conversion factor. So the factor that I would use would be pi over 180 degrees, and that gives me pi by 2 radians as my angle measurement in radians. And we'll do the same for 180 degrees and we get pi radians. 30 degrees will give us pi by 6 radians, and it is okay to leave your answers in simplified form as a fraction, because that's kind of what we really work with. Okay, we are not gonna put it in the calculator and convert it into a decimal. 60 degrees will give us pi by 3 radians, and 270 degrees will be 3 pi by 2 radians. Now let's try to do the same with radians to degree conversion. Now remember, we are given radians, so we want to get rid of radians. So the conversion factor that we will multiply by needs to have radians in the denominator. So we will multiply this by 180 degrees by pi radians, and that gives us 270 degrees. So half of a pi radian would give us 90 degrees. Negative of that will just give us negative 90 degrees. 10 pi will give us 1,800 degrees, and 100 pi will give us 18,000 degrees. So that is how you do your radian to degree or degree to radian conversion. Now if you're working with your calculator, please be careful if you're working in degrees to have the settings on degrees, and if you're working in radians, you need to make sure the setting is in radians. By default, your calculator is going to be in radians every time you reset it. Okay, let's move on to location of a point in the plane. Now, if I have a point in the plane and let's say its coordinates are 2, 3. Now, these coordinates that you are used to are actually called rectangular coordinates. And we are not going to try to use them anymore. We are going to try to find another way of coming up with location of a point. So we know that this point is at a distance r from the center or the origin, right? And we have done in the past that r is square root of 2 square plus 3 square, but we don't need to do that right now. And let's say the angle of rotation in standard position is theta. Now remember, standard position means that the angle is measured from positive x-axis in the counterclockwise direction. Now, if I am thinking of a point at a distance r from the origin, and it makes angle theta as angle of rotation in standard position, can you think of multiple points or even a second point that can have the same value of r and theta? So pause the video and think about how many points can you think of with the same value of r and theta. Well, I hope that you didn't come up with any other angles because there is only one point, okay? And which means that we can write the location of that point in form of r and theta. So I can write r and then theta. And remember the order. We first write the distance from the origin, and the second value is the angle of rotation in the standard position, and this is a polar coordinate of that point. So remember, rectangular coordinates would be 2 and 3. Polar coordinates would be the distance of the point from the center and then the angle of rotation in standard position. Okay, we are moving on to arc length and radius. So I have two concentric circles. That just means that two circles with the same center. And we have the first circle of radius r, and I'm going to draw another line of the same length, so radius r. The arc that it makes, let's call it s. Okay, now the angle that this arc length s makes with the center of the circle, let's say it's theta. So what is the relationship between these three variables? It is theta is equal to s divided by r, and we can say the angle of a segment is equal to arc length divided by radius. Okay, now let's use the bigger circle. So the bigger circle has a radius uppercase r, so we got uppercase r there too, and the arc length is uppercase s. Now it makes the same exact angle theta. So I can again use the same relationship to write theta equals uppercase s over uppercase r. But we know that both angles are exactly the same. So I can say that the ratio of arc length to the radius of the bigger circle is the same as the smaller circle, right? And from there we get the idea of proportionality relationships between corresponding points and arc lengths of concentric circles. Okay, let's move on to a practice problem. So Lulu wants to draw 20 points on the circumference of a 12-meter radius circle such that all the points are equidistant from each other, and we have to calculate the arc length between each point. Okay, now we know the relationship between arc length and radius is s is equal to r theta. Now in this case, radius is 12 meters, right? That's given to us. We're not given theta, but we do know that there are 20 points on the circumference. These 20 points are going to create 20 segments. So it will cut the circle into 20 pieces, right? 20 exactly same pieces. And we know that the total circle's angle is 2 pi radians. So then from there I can get angle for each segment, and that gives us pi by 10 radians. Okay, so now if I plug in these values in this equation, I will end up getting my arc length equals 6 pi by 5 meters, right? Now here is the thing, why didn't we use degrees? We used radians, right? We didn't use 360 degrees divided by 20, right? And we would end up with a different answer if we did that. The thing is that when you're working with S equals R theta, theta must be in radians. So remember that rule. If you are given angle in radians, then you can use S equals R theta. But if you're not given your angle in radians, you would have to first convert it in radians, and then you can use this equation. Okay, so now there are some important angles that would be nice if you know without actually doing the calculation. So you already know these because you use these angles a lot. Okay, so we have a circle. So the first angle, remember, we are always measuring them in standard position, is going to be 0 radians. And if I complete a full circle, that gives me 2 pi radians. How about half of a circle? Well, pi radians. How about half of that? Pi by 2 radians. What if I cut the other half, the bottom half? We get 3 pi by 2 radians. Now let's break the circle into even more segments. So the first one, this one here, this one here is going to be pi by 6 radian, right? Because I've split this first quadrant into 3 equal parts, right? So if I've split it into 3 equal parts, I'm gonna end up with each part having an angle of 1/3 of the 90-degree angle, or the pi by 2 radian angle, right? And that gives us pi by 6 radian. So the next one is gonna be pi by 3 radian. Okay, and then when we move to the second quadrant, we will end up with 2 pi by 3 radian, then 5 pi by 6 radian. Third quadrant, we will have 7 pi by 6 radian, 4 pi by 3 radian. Fourth quadrant, we will have 5 pi by 3 radian and 11 pi by 6 radian. Okay, now maybe these numbers seem a little odd to you, but if you think about, we went from 0 to this one, and we know that is pi by 6 radian, right? And all you have to do is add another pi by 6 to this, you get pi by 3 radian. Add another pi by 6, and of course we are simplifying it, right? So like this one would be actually, if you were doing so this one would be pi by 6 plus pi by 6, you get 2 pi by 6 here, right? This pen is really slow, so bear with me. There we go. And that gives us pi by 3, right? So the next one would be actually 3 pi by 6, then 4 pi by 6, 5 pi by 6, 6 pi by 6, 7 pi by 6, 8 pi by 6, 9 pi by 6, 10 pi by 6, 11 pi by 6, and then 12 pi by 6. Okay, so these fractions are just written in a simplified form, and it would be good if you can, over time, just remember these fractions. Let's try to write these in degrees now. So we got our first one as 30 degrees, 60 degrees, then 90 degrees, 120 degrees, 150 degrees, 180, 210, 240, 270, 300, 330, and 360 degrees. So remember, we had our special right triangles, 30, 60, 90 triangle, right? And that is why pi by 6 and pi by 3 radian angles are important angles, because you will see them a lot. Okay? Let's do some practice. So I want you to pause this video and then do the same thing as I just did. So you are just writing down in terms of radians and in terms of degrees what these angles are going to be. So pause the video, do the angles, and then play it again. Okay, so this is what you should end up having. And this time we have cut them into, so the first quadrant is cut into half, so you get pi by 4 radian, and so on. Okay, in terms of degrees, you will have these, and again, you know 45, 45, 90 is a special right triangle, and we see those triangles a lot, and that's why it is important for you to also remember that 45 degree equates to pi by 4 radians. That is it. Let's quickly wrap it up. So we know that angles can be measured in degrees and radians. The radian measurement of an angle is the ratio of arc length to the radius of the circle for the arc whose endpoints lie on the initial and terminal rays. We know we can locate points in a plane by using rectangular coordinates x and y, and now we have also learned polar coordinates r, theta. Okay, we also talked about radians to degree conversions. Also a circle, if a circle is divided into n equal arcs or n equal parts, then the angle measure of one arc is 360 divided by n. In terms of radians, it would be 2 pi divided by n radians. Now, if you're given an angle in degrees, the arc length, radius, and angle relationship is going to be s equals theta divided by 360 degrees times 2 pi r. But if you're given the angle measurement in radians, then the equation is just s equals r theta. Okay, remember that now you can convert degree measurements to radians by multiplying the degree measure by the angle by pi by 180 degrees, and you can do the opposite, go from radians to degrees by multiplying by 180 degrees by pi. And that is the end of this lesson. So remember, we covered lesson 6 and 7, and I hope this video was helpful. I will see you next time for lesson 8.